Many of the processes in a plant depend on electrical equipment. In order for this equipment to function properly, it must have a continuous, reliable source of electricity to power it. An electrical distribution system supplies power to meet the needs of process equipment. The distribution system consists of equipment that brings electric power into the plant, converts that power to usable voltages for process equipment, distributes the power throughout the plant, and protects components in the system from damage. As an operator, you're likely to work with electrical equipment on a regular basis, so you need to have a basic understanding of your plant's electrical distribution system. Many plants receive all of their electric power from an off-site source, such as an electric power company. The power that's supplied to a plant can be generated in a number of different ways. One common source of electricity is power plants that convert the energy in fossil fuels, such as coal, oil, or natural gas, into electrical energy. Off-site electricity may also come from nuclear plants, which harness the atomic energy produced by the splitting of an atom's nucleus. Another possible source of electricity is hydroelectric plants, which use the energy of falling water to generate electricity. In any case, once electricity is generated at power plants, it must be transmitted, sometimes over long distances, to the facility. Power transmission lines bring electric power into a facility. In this case, the voltage coming into the facility is 69,000 volts. Other voltages are also commonly used, depending on the power supply system and the requirements of the facility. Here, the incoming voltage is 34,500 volts. For most industrial customers, electric power comes into the plant at what is known as the main substation. Voltage can be changed from one value to another using a device called a transformer. A transformer increases or decreases voltage for various uses. At this plant, the main substation transformer takes the incoming voltage, 69,000 volts, and reduces it to a level the plant can use, which in this case is 13,200 volts. Overhead cables take the 13,200 volts of power from the main substation and distribute the power throughout the plant. The voltage leaving the main substation is often referred to as the distribution voltage. Plants can use different distribution voltages. Some other common voltages are 13,800 volts and 2,300 volts. However, since specific plant equipment may require lower voltages, the distribution voltage may need to be reduced further by transformers. Not all plants receive electric power from an off-site source. Some plants combine power from an off-site source with power they produce themselves on-site, or they produce all of their own power on-site. Some on-site power generating facilities are part of a cogeneration process, which provides the plant with electric power as well as process steam. Let's look at some of the ways that industrial facilities can generate electricity on-site. One way to generate electricity is by using steam that's produced in a boiler. With this method, fuel is ignited and burned in the boiler. Many boilers burn fossil fuels, but others burn fuels like wood chips or other combustible materials. In any case, the burning fuel releases heat or thermal energy, which is absorbed by water flowing through tubes in the boiler. When the water gets hot enough, it boils, producing steam. Steam from the boiler is supplied to a turbine generator set, which converts the thermal energy in the steam to electrical energy in 2 steps. In the first step, the steam is forced through a series of turbine blades. Some of the blades are fixed and direct the steam through the turbine. Other blades are mounted on a shaft inside the turbine. As the steam passes between the blades, an energy conversion occurs which causes the turbine shaft to rotate. In the turbine, the thermal energy is converted to mechanical energy. The turbine shaft is connected to the generator shaft. As the turbine drives the generator, the mechanical energy is converted to electrical energy. The output from the generator is electricity that can then be supplied to the plant's electrical distribution system. This particular generator produces 13,200 volts, but other generators can produce different voltages. Steam turbines aren't the only devices used to drive generators. For example, some generators are driven by gas turbines. Like steam turbines, gas turbines take energy from a fluid moving through blades. Gas turbines use hot combustion gas that's produced by burning a mixture of fuel and air. In fact, gas turbines are sometimes called combustion turbines. As the fuel and air mixture is ignited and burned, the hot gas expands and flows rapidly through the turbine blades. The thermal energy in the hot gas is converted to mechanical energy, which causes the turbine shaft to rotate. This, in turn, drives the generator and produces electric power. Gas turbines are often used for emergency purposes as a source of backup power. They provide enough power to keep essential equipment and services going until repairs can be made to the main power generation system. Gas turbines can also be used in combined cycle arrangements. In a combined cycle system, exhaust heat from a gas turbine is used to boil water and make steam for a steam turbine. Using an exhaust product from one turbine to provide heat for another turbine increases power generation efficiency. Diesel engines are also frequently used to drive generators. Basically, a diesel engine is an internal combustion engine that burns diesel fuel instead of gasoline. In a diesel engine, a fuel and air mixture is compressed and burned, much as it is in a car engine. This internal combustion turns a crankshaft, which provides a mechanical motion for a generator to produce electricity. Some plants use diesels as emergency power generators. Diesels can be set up to start automatically when the main power source is lost. In addition, some diesels are portable and can be used to generate power when other power sources are unavailable. In this topic, we saw how electric power comes into a plant from an off-site source, and we looked at ways in which power can be generated on-site. Now take a moment to try some practice questions on this material. For most industrial customers, electric power comes into the plant at what is known as the main substation. A substation is an area in which voltage is changed from one value to another. When steam from a boiler passes through a turbine, thermal energy in the steam is converted to mechanical energy. This causes the turbine shaft to rotate and drive a generator to produce electricity. In order for the electric power that's supplied to a plant to be utilized, it has to be distributed at the proper voltage to the equipment that uses it, wherever that equipment's located. That's where an electrical distribution system comes into play. The purpose of an electrical distribution system is to supply power to electrical equipment at its specified or rated voltage. The system has to meet the needs of a wide range of equipment, from large motors that operate at several hundred volts to standard electrical outlets that require much less voltage. Distribution systems also contain equipment that has a protective function. Protective equipment helps minimize damage to the system during abnormal conditions, such as short circuits, overloads, and voltage surges caused by lightning. Distribution systems vary widely, depending on a plant's power requirements and its processes. We'll look at one example, but your plant's system and the equipment in it may be different. Despite the differences, you should still be able to apply what you learn here to just about any system. We'll use this simple block diagram as a starting point for our explanation of a distribution system. The system represented here has a main substation, which takes incoming power and reduces its voltage, as well as two smaller substations called unit substations. The unit substations reduce the voltage from the main substation to levels that parts of the plant can use. The distribution system also has various loads. Load refers to a circuit or piece of equipment that uses the electric power. The electric power flows through the system along different paths or circuits. In this system, the distribution voltage leaving the main substation is 13,200 volts, or 13.2 kV. kV stands for kilovolts, or thousands of volts. The part of the system that carries the 13.2 kV is called a bus. A bus distributes power in an electrical distribution system, and it operates at a specific voltage. The 13.2 kV bus feeds the two unit substations, which reduce the voltage to a level that's usable by the equipment being supplied. This unit substation reduces the 13.2 kV to 2.3 kV. This part of the circuit is a 2.3 kV bus, since it supplies 2,300 volts to these loads. Now, this unit substation reduces the voltage from 13.2 kV to 480 volts. This part of the circuit is a 480 volt bus, since it supplies 480 volts to these loads. Most electrical distribution systems have several buses at different voltages. They may also have more than one bus at a given voltage. For example, several 480 volt buses may be needed if the plant has a lot of 480 volt loads. A plant's electrical distribution system is often represented on electrical diagrams. These diagrams typically include information about bus voltages and system components, which can help operators pinpoint the source of a problem. This diagram represents the system we saw earlier. Voltage comes into the main substation at 69 kV and is reduced to 13.2 kV. The voltage is reduced by the main transformer, and this is the electrical symbol for a transformer. Now, this symbol represents a circuit breaker. Circuit breakers have two basic functions. First, they protect loads from potentially damaging conditions by automatically tripping, that is, by interrupting current flow. After the abnormal conditions have been corrected, circuit breakers can be reset to restore a path for current flow to equipment that needs it. Circuit breakers also provide a means of manually isolating loads from their source of power. This helps to protect personnel when maintenance is needed. The electrical diagram for this system also shows the buses that we mentioned earlier, including the 13.2 kV bus, the 2.3 kV bus, and the 480 volt bus. Let's take a closer look at the 2.3 kV bus. This transformer converts the distribution voltage, 13.2 kV, to 2.3 kV. There are circuit breakers on each side of the transformer. The 2.3 kV bus supplies power to 3 different loads. 2 of the loads are motors that are fed directly from the 2.3 kV bus. Each of the motors is protected by a circuit breaker. The other load is a separate bus, in this case a 480 volt bus. A transformer reduces the voltage from the 2.3 kV bus to 480 volts. The transformer also has circuit breakers on each side. 2 motors serve as loads off the 480 volt bus, and each motor is protected by a circuit breaker. Now that we've looked at the 2.3 kV bus, let's do the same for this 480 volt bus. As you can see, a transformer reduces the distribution voltage, 13.2 kV, to 480 volts. The 480 volt bus provides electric power to 2 transformers. One of the transformers reduces the voltage from 480 volts to 240 volts for a lighting circuit, which powers the lights in the area. The other transformer reduces the voltage from 480 volts to 110 volts for a circuit that supplies several 110 volt loads in the area. One load is a motor. The device that protects the motor is a fuse. A fuse works much like a circuit breaker. That is, it interrupts current flow if the current flow exceeds a certain value. But unlike a circuit breaker, a fuse can't be reset. When a fuse operates, it burns open and has to be replaced. Electrical diagrams can be extremely helpful when you're trying to isolate problems with equipment. For example, suppose this 110 volt motor stops working. After ruling out any mechanical or electrical causes at the motor, you can use the diagram to investigate possible causes in the system. Now, there are different ways to troubleshoot a problem. One way is to check the fuses in circuit breakers to see if a fuse blew or if a circuit breaker tripped. The diagram helps the operator determine where the fuses in circuit breakers are for a particular system. By working backwards from the motor, it's possible to figure out where the power is being interrupted. As an operator, you hear a lot of talk about safety, and you're likely to see warning signs around the plant. One thing you should never do is take safety for granted. Many people think that accidents can never happen to them, that safety's for other people. But carelessness and improper shortcuts are two big causes of industrial accidents and injuries. Safety is especially important when you're working around electricity. You can't see electricity, but if you don't take precautions, it can be deadly. Your plant probably has rules and guidelines to help people do their jobs safely. Follow these rules to the letter when you work around electrical equipment. A knowledge of basic electrical safety rules, combined with a good understanding of your company's policies, can reduce the hazards related to electrical equipment. Your plant probably uses a series of overhead lines to carry electric power. At some point, you may come across a downed power line. You should always assume that downed power lines are live, and a live line can electrocute you or cause a fire. If you see a downed line, report it immediately. Cables that carry electric power at a plant may be installed in a protective pipe or tubing called conduit, and most cables and wires are insulated. However, cuts or breaks can decrease the effectiveness of the insulation. This could result in a fire, an electrical shock, or arcing. Arcing is the discharge of electricity across a gap in a circuit. Another potential hazard is a leak in a pipe. Leaks in pipes can result in liquid coming into contact with electrical equipment. You can get shocked, for example, if you're trying to identify the source of a leak and you accidentally touch energized equipment. In addition, some liquids can start a fire when they get on energized equipment. Be careful anytime you have to check electrical equipment closely. In some cases, you may smell insulation burning or see arcing, which tells you that current is going where it's not supposed to. If you work around electrical equipment, it's possible you may be faced with emergency situations, such as treating a victim of electrical shock. Your company may have its own specific procedures for emergencies, but here are a few general guidelines to follow if you're trying to help an electrical shock victim and the victim is touching a power source. First, try to cut off the power supply if possible. If you can't do that, try using a non-conducting pole or rope to separate the victim from the electrical source. In some cases, you can even use your belt. But what you should not do is touch the victim with any part of your body. If you touch the victim with any part of your body, you may get an electrical shock too. We've just seen some basic guidelines for dealing with an electrical shock victim. In general, the goal is to isolate the victim from the source of electricity without creating a path for current flow through yourself or others. Learn your company's procedures and follow them to the letter if you're ever faced with this situation. Another hazard that you may have to deal with is an electrical fire. Electrical fires can happen for many reasons, and it may be part of your job to respond to them. Generally, the first thing to do is report the fire. Reporting the fire will set in motion other emergency actions, such as isolating circuits to prevent injury and equipment damage. Then try to cut off power if possible. This takes away the source of ignition. If you're going to put the fire out, be sure to use the right type of fire extinguisher. Fire extinguishers are classified by the type of fire they're designed to extinguish. A Class C fire extinguisher is used for electrical fires. Class C extinguishers often contain carbon dioxide, CO2, which is ideal for electrical fires because CO2 puts out the fire without conducting electricity. You should never use water to put out an electrical fire. Water conducts electricity, and it can cause an explosion or create hazardous paths for current flow. By now, you should be aware of the main concerns related to electrical fires. However, you should still learn the procedures and safety measures that apply to the equipment and hazards in your plant. Our focus in this topic was on power distribution. We looked at the main components in a typical electrical distribution system, and we explored some key safety issues associated with electrical equipment. Take some time now to try a couple of practice questions on this material. Now, this symbol represents a circuit breaker. Circuit breakers have two basic functions. First, they protect loads from potentially damaging conditions by automatically tripping, that is, by interrupting current flow. After the abnormal conditions have been corrected, Circuit breakers can be reset to restore a path for current flow to equipment that needs it. Circuit breakers also provide a means of manually isolating loads from their source of power. This helps to protect personnel when maintenance is needed. Another hazard that you may have to deal with is an electrical fire. Electrical fires can happen for many reasons, and it may be part of your job to respond to them. Generally, the first thing to do is report the fire. Reporting the fire will set in motion other emergency actions, such as isolating circuits to prevent injury and equipment damage. Then try to cut off power if possible. This takes away the source of ignition. If you're going to put the fire out, be sure to use the right type of fire extinguisher. Fire extinguishers are classified by the type of fire they're designed to extinguish.